So today, that's better, isn't it? Woo! Yeah. Today we're going to talk about deployment, the sort of last bit in terms of the picture. We talked a lot about, how do we conceptually design databases? We've talked about data mining, what we use. We've talked at length about SQL, the different types of SQL we use, all that kind of stuff. We talked about security on Tuesday, so you're all elite hackers now that you know a little bit of SQL injection. And today we're going to talk about deployment. How do we actually deploy things in the real world and do it? Before we do that, let's just have a quick chat about your project work, which I'm sure all of you have basically finished by now. So you voted on some topics to cover, and what we're doing is as of next week, so next week we have 3 lectures. We're not doing any new material, we'll just be recovering. They've been removed from Active Campus, so they're not required, they're optional lectures. Next Tuesday, I'll do Select with Joins, so we'll go through and do Select with Join, and then we have Wednesday and Thursday free as well. So email me if there's topics you want to cover. If not, I'll decide what I think is worth doing. Maybe we'll go through, because for your project work, I kind of think creating tables with relational keys, which we did on Wednesday, and Select with Joins are probably the 2 most troublesome ones, but I'm quite happy to go through any topics you want, so drop me an email and tell me what you want to do. There is an online thing, which I've shown you previously, called AME Bots. I sent you an email about it, and there's links to it in the resources online. It is an automatic marking engine, so it will give you formative feedback using roughly the same criteria that we will use to mark your assignments. You can upload 3 files to it, which are exactly the file and the format that we need for the main assignment. A schema file, a data file, and a queries file. Schema file containing all of the instructions to just create the database. The data file containing all of the insert commands to create the sample data in the database, and the queries file being a file that contains 10 select queries in order, which are questions 1 to 10. The bot will run them. It will do a whole series of tests, which are a subset of the tests I'll use to mark them, and it will give you output. And now, as of today, it's been upgraded to be colourful as well. So any results that you get the full score for that element will be green. Any which you get less than the full score, more than 0, will be yellow. And any that score a 0 will be red. Read the notes, there's lots of caveats on it. It's only indicative marking. If you don't upload a data file, it won't test the data file. So therefore, you could score 100%, but if you've only uploaded one of the 3 files, then when I come to test it, obviously you still won't score the full marks. Will the extra lectures be recorded? No, I'm afraid not. And the reason why is because they are just recovering the material that we've done before, and I'm doing it quickly. So, for example, we did creating tables on Tuesday. In 40 minutes, I did what was a sort of hour and a half's worth of material. So I don't really want to record that and upload it, because if you were here, you might have got something out of it. If you weren't here, you're better off watching the full detailed version of the lecture rather than anything else. Optional, yes, they are. Can I talk about the Java program part of the assignment? Yeah, we can do that. We can definitely do that one of the days, because we sort of showed it to you. So maybe we'll do that next Wednesday. That's all right. Or Wednesday's a bit of a funny one, isn't it? Would you rather do that on the Thursday when most people will actually be here? Yeah. Okay, so we'll do Java next Thursday, and any other open questions on the project next Thursday, and we'll find another topic Wednesday. What format the file's meant to be in? They are .sql files, which is exactly what it says in the project format. A .sql file is a text file with the .sql extension. Okay, you got any questions? Some people already have, but feel free to use today's meet to ask them as we go along. So let's talk today then about the challenges inherent in live deployment. How do we go from a system that we have built and we're running it, and we're running it on our own laptops or in our own lab, and we now need to expose it to the outside world. So we had a chat on Tuesday about security. So some of the things that you would always have to do to try and keep your system secure. You'd lower your attack surface. You'd only expose the ports and the bits of it that you need to. Everything else you'd hide behind firewalls and security procedures. But what else can you do to actually sort of deploy it live? So we're going to talk a little bit about backups and about replicas, the difference between them, read-only replicas, hot and warm swapping, locations, and about demoting and promoting of data that we have problems with the sheer volume of data that we've got. How do we cope with the fact that we've got 20 billion records and we don't really want to store all of that on high-speed SSD? One of the terms that we use a lot in systems deployment, and for those of you who are on the CIT pathway, assuming I don't get fired this summer, which will be a miracle, but if that doesn't happen and I've still got a job next year, you'll do a module that I teach in the second year called Systems Administration and Maintenance, where I will bore you rigid. These off. Have I just been talking with those off? Did no one want to tell me that? Why are they off? Does anyone know anything about computers? Luckily, nothing is needed on the slides so far. Why? But why are they off? It says they're on here. I'm happily looking away on here. This is comedy gold, this, isn't it? If you watch the recording, then you'll see nice slides. I'm going to turn this system off and back on again. If that doesn't solve it, we are buggered. Right, this will go on for 3 minutes. You're right, I don't need them. I don't need them. I'm entertaining enough. Look at me, not at the slides. Here we go. This is going to be good, isn't it? Resilience. Resilience is a term that we use in terms of systems delivery, and what we mean is how resilient is the service. I want to produce this service, and I want it to survive. I want it to be resilient to things happening. As people, we use the term resilience. Some of our friends are much more resilient than others to things happening. What we don't want is a service or a system that the first problem that occurs, someone puts the wrong data into a field, it falls over and it fails. So resilience is all about trying to keep our services running regardless of what the problems happen to them. And really it comes down to a nice euphemism I like about eggs and baskets, is that if we put all our eggs in one basket, it better be a bloody good basket. Because if that basket fails, then we're going to end up with eggs on our feet or whatever. But the idea that hard drives fail. Hard drives fail very commonly. I'm sure most of you have had a hard drive fail over the years. I've certainly had a lot fail. Servers fail. Servers crash, servers break, operating systems break. Data centers fail. We can have an entire data center catch fire, sink, whatever. So resilience is all about trying to spread the risk, that rather than relying on one hard drive in one server in one location, we actually rely on many hard drives, many servers, many locations. If one of them goes down, if something bad happens to one of them, we don't really care and we can carry on. And another threat in the modern world is not just the systems failing, it's not a technical threat, but social threats. We could have legislation change, we could have a revolution in our very cheap hosted data center. We open the door, look outside, and there's a revolution going on. And we can also have things happen like hackers attacking our system. Either a denial of service attack or an actual targeted specific poisoning attack where they actually get in and get our data out or put illegal data in. One of the approaches that we can take to try and mitigate this kind of thing going wrong is to take backups of data. We should all do it anyway. Hands up who backs up their hard drive. Well done. Hands up who lives life dangerously and doesn't back anything up. Good for you. I used to live dangerously until my luck ran out and I lost a lot of data. Of course, nowadays it makes life simpler. So I mean, I have my laptop here. I plug that in my office. Time Machine backs it up, but actually all of my core files are on Dropbox or on OneDrive. So that's all backed up. It's all cloudy. But we should back up our data. So one approach to saving our data and securing it and making sure that our servers continue to run is purely to back up our data, to actually back it up and ensure that we can continue to serve it if something happens. So backing up data mitigates against local loss. If we lose our files, so I'm going to turn this on now. Is it going to work? 45 seconds. Right. If we back our files up, if the servers go, the hard drives fail, it's not necessarily a big problem. We haven't actually lost any data because we have another copy of it. My hard drive fails. Well, okay, I haven't lost anything because I've got another drive with all the data on. But they're not really ideal. If we store them off site, then it mitigates against site loss. The world is full of people that take backups, then leave that drive plugged into the computer. Electricity surge takes both out. Or they take the drive out and they put it in a shelf next to the computer, data center burns down, both are lost. Commonly you would take backups off site, you would actually take them away with you. Come on. Turning it off and on again always works. There we go, look at that. See, you need resilience. We got two projectors, they both fail at the same time because we only have one box in the middle. But so backups mitigate against these things happening. And we have a copy of our data. If we take them off site, it means that theoretically we could have a asteroid hit our data center, or it could burn down, and we would still have the data. As I mentioned to you, they're not ideal because we just have the data. We don't actually have a service. We just have a copy of the data in there. And there's lots of other things we can do. And we can also keep backups for a certain period of time to make sure that we've got a copy from last year in case anything has changed or happened. Now, backup scheduling is a bit of an art form, apparently. People have written PhDs and books about it, and there are people whose job it is full-time to worry about what order we back things up in, which I'm sure are great fun to go out to the pub with. But really what we want to do, all we want to do is we have a server, I want to back up the data on it, and I want to back it up as flexibly as I can for the minimum amount of cost. I don't want to buy 1 million hard drives to back up. I want it to be easy and cheap in order to back it up. So one of the example rotations that's very, very commonly used is called grandfather, father, son, where we have a period of time where we, like daily, we have a drive that we back up every day. We also have a drive that we use every week, and then we have a drive that we use every month. So the idea is that we increase the period of time. So you can see this in a nice handy animation that we've created, which is why I'm glad the projectors are working, because I wouldn't like to do this through the medium of dance without a projector on. So we start off on a Monday. We have a backup that happens on that Monday. We have a tape or a drive or something that we store Monday night's data onto. We have another drive that we store the data on for Tuesday, another drive on Wednesday, and another drive for Thursday. So by the time we've reached Friday, we've got 4 days worth of data, and at any point you could say to me, I need the data as it was on Tuesday night, and I can go, okay, here you go, and pull it out. Fridays are a little bit different. So on Fridays we use a different tape. We call this Friday number 1. And then we carry on. We go out for the weekend, we go to the pub, we go crazy, then we come back in Monday morning and we start all over again. So next week, what do? On Monday, we use the Monday tape. On Tuesday, we use the Tuesday tape, and so on and so forth. So we're overwriting the data that was stored the previous week. We get to Friday, we use the second Friday tape. The third week, we reuse Monday, Tuesday, Wednesday, Thursday. We use the third Friday tape. And then on the last Friday of the month, we use the same tapes during the week, and we use a monthly tape at the end. The following week, standard Monday, Tuesday, Wednesday, Thursday, and now we rotate our Friday tape round to the front. So at any point, I will always have the last 5 days in daily increments, so I can give you every one of the last 5 days worth of backups without any problem. I will also have the last 3 or 4 Fridays, so the last 3 or 4 weekly backups, and I will have probably a year's worth of monthly backups. So by rotating these tapes, actually what we end up with is we end up with only 19 tapes or hard drives or whatever it is we're using, and yet we can back up across the entire year. For the previous week, we have backups every day. For the previous month, we have backups every week. And for the previous year, we have backups every month. So that will give us a reasonable amount of granularity in order to go into. And if something happens, if say in April we close our books, or we get hacked, the FBI are investigating us, whatever, we can just take the most recent backup tape out of rotation and put it in an evidence locker, and then just put a blank tape back in and carry on, so we can take a tape out of rotation. So that's backups, and there's lots of different ways in which we can back up data and schedule it. But it's not quite as simple as just synchronizing files. So we need to take the backup. So the first thing we need to do is we need to actually copy the data files. Now, if you have a MySQL database, it's running. You'll find that there's a folder on Linux, it's var lib databases, I think, or var lib MySQL databases. And in there, for every table in your database is a .mdb file that contains the binary copy of all the data and the schema and everything for your table. Now, you might think, well, okay, we can just copy those files. If I copy those files into a directory on another computer, they'll appear by magic and we can just use it. That is true, apart from the fact that while the database is running, those files are open. We shouldn't take copies, we shouldn't read files that are open at the time, because we could well take a copy that turns out to be terribly corrupted. We can't read it purely because it was open and halfway through being written at the time. We can get around that, we can stop the database. So I'm going to take a copy of the database files. First thing I do is I stop the database. Well, that's okay. The files won't be corrupted, they will be complete, but I've got to have downtime for my service. All right, let's export the SQL. You've all seen how to do that in PHPMyAdmin. There's command line tools to do it. We can just export all of the SQL, the schema, the data, all of that. That does work, but it can take a very, very long time. And also, the table data is nice and compressed and binary. The SQL is huge, it's verbose, it's very, very big, and it's poor to do. Also, the problem with backups is I've backed up the data, but when the server fails, what do? I still don't have a service as such, do I? I don't actually have anything working. All I have is a hard drive with a copy of the data in and a melted server that used to run a database engine. So I actually need to recover that data. So I still need another server. I need to go and buy a server, install the operating system, install MySQL, install the backup manager, plug the backup drive in and copy the data across. So I know I've got a copy of the data, but what it doesn't do is keep my service running. Those couple of days where I'm waiting to order the server, configure it, set it up, nothing works. And the alternative is, well, okay, I keep an entire spare set of hardware ready. It can be quite expensive in order to do. Let's have a look and see if anyone's asked any amazing questions. How do you start? I missed the introduction to it. I don't know what you're talking about. How do you do the required index and unique in SQL? So required would be null or not null. Index, you add an index at the end. Unique, the only unique fields in the project are primary keys, which will be unique by themselves, but there are other ways to make any keys unique. Still after that Johnny Bastardo scan, can you put it on QOL? I'm afraid for money, yes, but I'm selling replica prints of that. I'm going to get Johnny Buster to actually sign it, and then we're good to go. So backups are a problem. Backups are fine. We should do them, we must do them, we have our data, but they don't offer us full resilience. If the server fails, if it catches fire, the data center fails, we still don't have a service. Our users still can't log in. Their data might be safe. We can repair it. We're not going to lose anything, but we're still up a creek. So one of the other ways in which databases can be resilient is through the use of a thing called replicas. And a replica is basically a live, up-to-date copy of the database that's kept synchronized in real time or near real time. All the commercial database engines, so Microsoft SQL Server, Oracle, DB2, you name it, they will all have ways of synchronizing databases, having multiple databases where you just tell it to keep them synchronized and they do it for you. But to understand it conceptually, to look at things like MySQL, the SQL log is probably the easiest way to understand. It still works, it's still used quite widely in terms of replicas, and it goes. And very simply, all we do is that whenever our database receives an update query, whenever we get a query that changes data, so either an insert, an update, a delete, something like that, maybe a drop table, create table, we pass that same query on to the other databases. So we have 5 or 6 databases. We send a query to one of them that writes, and it just passes them on to the other ones, and off we go. Now, replicas can also be read-only. That's pretty common that they're one way. Or they can be read-write, where data is synchronized both ways between the databases. The most common example, though, is a read-only replica. So what we have is we have a database server, RDBMS server. We call it generally the master because it is the one that is the authoritative copy. And on it, perhaps we have a customer table that has a couple of records in it. And what we want to do is we would like to have another replica of this database on another server. So we set up another server, we'll call the slave, server B, and we have exactly the same database on it. So the two are now synchronized. We go to the outside world, and customers make changes to the master server. So what happens then? A query comes in from a user, in this case to insert data into a table. The query happens, the table is inserted into. The master server generates a new update query, which will carry that update. It has all the changes made in that update, including any unique ID fields that have been updated, anything like that, and passes it, logs it, and passes it along to the slave server. And the slave server, in turn, executes the SQL, and now everything is back in sync. So that's the simple way in which we can have many, many servers all maintaining exactly the same image and the same version of data within them. We do it by replicas, and we do it by just logging all of the queries that come in and passing them on. Because if we start at the same condition and we all execute exactly the same queries in exactly the same order, then our end state should be exactly the same. These can go wrong because we might have the wrong version of SQL between things. We might have something happen, there might be a delay in them, but generally it works pretty well. And we can just take that SQL log and pipe it in real time to all of the other servers and cascade it around the network. So we can have one master that we make changes to, and we can have 20 or 30 other servers which are up to date and keep the changes to go into. So two-way replicas are more complicated. If we want to both read and write, two-way replicas are where we have a number of instances of the database. I can make changes to any one of them, and that change is reflected in all of them at the same time. It's a very interesting problem to try and solve. It's quite an advanced distributed computing topic. If any of you are lucky enough to stay on and you don't get jobs and choose to do an integrated master's or come back and do an MSc, you may well cover distributed computing and synchronization. So we're not going to go into it in any great detail because it is quite a headache. It's quite an interesting problem. Like if I have two databases and I insert data into both of them, how do I guarantee that the unique ID remains the same? How do I guarantee that they're not both allocating the next auto increment number? So there's all sorts of problems which are fascinating, I'm sure you'll find and come into. But you can have read-write databases. And if you're working with, as I mentioned, if you're working with what I would call an enterprise-grade database, SQL Server, DB2, Oracle, it'll do it for you. You can set it up and you can just say, I want a cluster of databases. I want 4 or 5 databases. I want the same data. I want them all read-write, and it will handle all of that for you by pre-allocating numbers and space within it. So replicas are generally quite a good idea. Even read-only replicas are quite powerful and can offer a speed boost. Many data systems are very, very, very read-heavy. If you think about something like Facebook, 99.99999% of the requests to Facebook are to read content. When I load my news feed, the tree of queries that go out to all the different people and sponsored sources and this and that and the other to build my news feed, there's a huge number of them, and they are all read. It might log that I've viewed things, it might log that I've clicked a like occasionally, but that's one write against a huge amount of reading. If you think about how much time you spend stalking people on Facebook and then accidentally click like on a photo from 6 years ago, that's one write, but many, many, many nights of reading over their content. So most data systems are very, very read heavy. You know, Google logs my search, but the vast majority of what it's doing is it's doing a huge complicated read query across all of its data and displaying me results. So if we use read-only replicas, we can speed everything up, because instead of now reading from one database, what we can say is, okay, you have to write to one database, but you can read from any. So I'm no longer limiting reading to one. I can have various replicas around the network. They're all synchronized over a back network channel, and I can read from any of them. How quickly you choose to update them is up to you. You might have real-time updates. You might have slower updates. We'll talk a bit about data volume in a minute. But I don't know about you, but I often see this on Facebook because Facebook pushes updates out slowly through its network. It doesn't have everything real time. It couldn't do it. So you might like a post. 5 minutes later from another computer log in, you don't appear to have liked that post. Click refresh and suddenly your like appears. What's happening there is that your data, your changes, are propagating through the network, and the replica that you are reading off at that time hasn't yet been updated with everything within it. Some heavy discussion going on at the back there. I'm sure about database replicas. I'm sure that's what it is. So replicas are quite important, and they are quite a good way of synchronizing data. What happens if a server crashes before the query is sent to the replica? It doesn't get there. So you're absolutely right, there is a potential there for an error to happen. The server comes in, it receives the query, it updates the table, and then it crashes and doesn't pass it on. All I would say at that point is that server A has crashed, therefore there is no copy of the data having been sent out, so the transaction probably could be regarded as not successful. And I look a bit like Raymond van Barneveld. Who's Raymond van Barneveld? I'm not going to Google it. Right. So replicas are quite important, and they are a way of having data stored in different places at a different time. And replicas offer a potential for resilience because they represent the same state as each other, or at least they should, unless anything crashes. If the master server fails, we can just promote one of the other servers and say, okay, you've got an up-to-date version of the data, you are now the master, you now push out the changes. So we can keep the network up even if one of the servers or more than one of the servers has failed. If they're read-write replicas, we can transparently fail over. We don't even need to change it. We can just change which connection the users are using in order to connect through to it. So it's dead simple as it goes along. However, replicas on their own offer no interruption to service, but they are not sufficient as a replacement to backups. The purpose of backups is to keep an authoritative copy of our data so that if something bad happens, we can go back and we can get our data back. If I have 50 replicas and a hacker instructs my one server to drop all the records, and that propagates as it should seamlessly around our network, and all 50 servers drop all the databases, we're still in trouble. It happened live, there's no interruption to service, all the servers are still up, but we've got a problem. Likewise, if we discover that a hacker broke in 3 months ago and created a user account, which is quite common, they created another admin user account, if we've just got replicas, all we've got is an up-to-date version of the poison data. Without backups, we can't go back and recover ourselves to a time in the past when it worked. So a few of the terms then that we talk about in terms of resilience, you'll come across these if you deal with IT service management. We talk a lot about things like hot swap. And a hot swap basically means something we can change without turning the power off. Servers always used to be very much not hot swap. If anything went wrong with the server, you'd have to turn it off, disconnect it from the power, take the top off and change anything inside it. Modern servers are incredibly modular, and a lot of things inside servers are hot swappable. So very commonly, hard drives are hot swappable. You can take them out, put new ones in. Power supply units are hot swappable. There are 2 PSUs in most servers, or some HP servers anyway, and you can unplug one, pull it out, put another one in. In some enterprise level servers, RAM is hot swappable and processors are hot swappable. So you can actually change them in and out without turning anything off. So these are quite impressive things, and it means we can tolerate a hardware failure, we can swap the part, and we have zero downtime. In terms of databases, in terms of systems, what we mean by hot swap is that no downtime is noticed. We haven't turned the service off. We're having a problem with this server, so I just point all our users to use this server. They don't notice any interruption, everything is fine. That's a hot swap. It's dealing with things without any interruption to the server. A warm swap, or what we really don't want, a cold swap, is something we can change with a brief interruption to service. So in terms of physical hardware, we might be talking about changing a power supply unit which isn't redundant, turn the computer off, slide it out, slide the new one in, boot it up. So we're looking at sort of a minute or two's downtime. In terms of databases, we might be looking at, okay, what are we going to do? We're going to have to reprovision our read-only replica as a read-write replica and reconfigure something to point to it. So we're looking at a couple of minutes of interruption. Cold swap is, of course, the worst possible, and that's when we have to turn everything off and start again from scratch. Kind of thing being our server has failed, we have a backup, but we have no other new server. We have to phone Dell, order a server, get it, install the operating system. So we're talking about a downtime of days rather than minutes. So we want to try and minimize that, and wherever possible, have it so our systems, whether they are physical hardware or whether they are databases, can just be changed over as we go along. He's a Dutch darts player. I've always thought I should have a career in the darts, but only in Holland. So that's weird. Wish I could back up my love life. Don't we all? Don't we all? Don't tell anyone, but replicas is the answer. It's not true. It's not true. It's a lie. No, no. Anyway, yeah, we all wish we could step back, don't we? Oh God, where have we gone wrong in life? Right. You're all young. Get out now. Leave while you can. No, come on, Dave. You can do it. Don't break down again in front of them. This is what happened last time. New city, new university. You can do it. Okay, server locations. Let's talk a bit about server location. Where do we put our servers? So one of the terms that you come across in IT service management nowadays is on-prem. I hate it. I hate people that shorten words for no reason, unless I'm doing it. But people talk, oh, it's on-prem, it's off-prem. On-premises, because premises was such a long word that we had to shorten it. So in the old days, everything was on-prem. It was on the premises. We would have a server. I'd ring a person, buy a server, have it delivered, put it in a room that was called a machine room, a computer room, and later a data center. Stick it in. We would generally own it. We might lease it, but it would be our responsibility, and we'd install everything on it, and we'd have to feed it power. We'd have to water it with nice cool air, and we'd have to keep it going. And we were responsible pretty much for everything. The network connection, the operating system, the database server, the application server, the hard drives, you name it. We had that go on. And one of the attractions of this model was that we could go and we could physically kick it. People like to go and look at servers. They like to go into rooms with lots of blinking lights and go, this is your £100,000 investment, this thing here, this box in the corner that's got all the lights on. And we can do it. But one of the issues really is that we're probably not an IT company. If we're a airline or a bank or whatever, we're not an IT company. We don't actually maintain servers for a living. And what we're ending up doing is we're ending up buying expensive servers, paying expensive salaries of IT people to maintain servers we don't understand, paying a load for the internet links to come into our building where we don't really need high-speed internet links, taking ages to set up and being quite responsive. So one of the questions that came up always was like, why can't we outsource this to someone else? And over the last few years, since sort of 2009 onwards, we've seen a huge rise in what's colloquially known as cloud computing. And cloud computing basically is putting our software on someone else's computer. There's nothing fancy about it. It's not clever. Cloud means I don't want to run it on my laptop. I want to run it on your laptop. It's your responsibility to run it. You are now the cloud. It's an amorphous blob of something that we don't control, and we throw our data into the cloud. So the servers, the hard drives, the network links, the infrastructure, the power, the air conditioning, the data center, instead of that being my problem, that's now someone else's problem. It's Google's problem. It's Amazon's problem. It's someone else's problem entirely. And hopefully, I pick someone who knows what they're doing. There's an awful lot of cloud companies out there, and there's an awful lot of cloud disasters where just because it becomes someone else's responsibility doesn't mean they're going to do a good job. It's still our data, it's still our services, it's still our customers, and customers aren't going to be happy if they can't access our service and I go, oh, well, it's nothing to do with us. We found a very cheap cloud provider from Venezuela who would promise to look after your data and run it on a Raspberry Pi. That isn't really going to wash, so we can put it up to some other people. Now, there are, of course, advantages to cloud, several advantages to cloud. Primarily, it's incredibly quick to provision. So the life cycle that I used to have when I had a proper job of getting a new server was we'd go and we'd get a quote and we'd buy a server from a service provider and they would send it out with a courier and we would have it installed in the machine room. Then we'd install an operating system, then we'd do this, then we'd do that. It would cost a lot of money to buy it, cost a lot of money to maintain it, and it would take a lot of time. Now, if I go on to DigitalOcean, AWS, Google App Engine, whatever, Heroku, I click a button and I say, I would like a new server, please. I would like it to have 16 gigs of RAM, this processor, go. And within 30 or 40 seconds, it's less if it's a virtual server, it's now available online and it's provisioned for me. As I say, the big advantage of cloud is that it's someone else's problem. I don't have to worry anymore about network infrastructure, gateways, ADSL backups, leased lines, fiber, any of this kind of stuff. All I need to say is, here's my web address for the service, make it go to a server that you're running the remote infrastructure. It's also incredibly cost effective. Buying servers is hugely expensive. Buying a laptop can be anywhere now from sort of 300 to 3 grand. Buying a server, a decent enterprise server, you're starting at 3 grand and going up from there. So there's a huge capital expense in buying this big lump of iron to put in your machine room. If I rent them, if I pay you as a server company £5 a month rather than £5 up front, then it's very cost effective for me. And one of the big rises in cloud, and one of the reasons why it's so popular, is elastic computing. And this is where Amazon started off and came into their own, and we could talk about all this for ages. But elastic computing is basically, here's your computing load, and it's elasticated. We can make it bigger or smaller as we need to, and we can do it automatically. So we can have a service that I automatically say to Amazon, if this server loads above 80%, spin up another one, and spin up another one, and spin up another one. As long as my credit card keeps paying them, because they're not doing it for fun, they're doing it for commercial reasons, I can carry on provisioning database servers. So I can set up my replicas, my database. I'm running with 1,000 users. I have 2 servers. It costs me £10 a month. And then suddenly I'm on the front page of something. I have 100,000 users. I haven't even had to deal with that. Automatically, Amazon have spun up loads more servers because we're getting a lot more traffic, and the elastic compute engine has dealt with it. There are disadvantages, however. It's very risky. I don't own it anymore. The risks aren't mine, they're yours, but the risks are still mine if you mess it up, if you balls anything up as it goes along. We have a lack of control over data and infrastructure. So GDPR is a big thing at the minute, General Data Protection Regulations. Where is our data? If it's in a data center in my building, I know where we're storing our data. If I trust it to Google, where's the data being stored? Is it in their Dublin data center? Is it in the America? Do they guarantee it? Will they guarantee it? How do I know where it's being stored? What are the legal issues with it transferring across borders? The infrastructure is often invisible. I have no idea if it's any good or not. There's a big web hosting company called GoDaddy. They advertise on the TV. They're a huge monster. A few years ago, it turned out that they were using basically the cheapest shop-bought seller-on PCs as their hosting providers. People, insiders, blew the whistle with photos of these sort of very crappily provided shuttle PCs running their hosting. I don't know what the infrastructure is. If I'm buying it myself, I have some idea of the quality that we're putting in. And critically, it might be their infrastructure, but it's our data, it's our customers, it's our jobs on the line if that fails. One of the other things to consider when dealing with data is where physically in the world is it going to be. So I mentioned there's legal issues with it. There's also issues to do with speed of access. So putting servers around the globe in many senses makes sense. So Google have data centers all over the globe, not just for resilience, but also so that when I access a data center and I access Google's website, I'm not having to go all the way to California in terms of data hops. I'm accessing probably Dublin or London, somewhere like that. So it's physically closer, which knocks a couple of milliseconds off every single request, which soon add up. Geographic distribution also reduces risk from interruption. If I have data centers that are geographically far apart, if a tornado hits one, it's unlikely to affect another. There are lots of stories from the Katrina disaster in New Orleans, the World Trade Center attacks of 9/11, where data centers were knocked out in, very spectacular, horrific ways. And some companies, that would knock them offline. Other companies carried on functioning because they had geographically distributed data centers that they could split things between. And it's often we want speedier, more cost-effective service, so we have data near you so I don't have to send your data and pay across the network. So the last thing we're going to just consider today is we're going to talk a little bit about data demotion. So there's a problem with data. This is revisiting, I think, what we talked about either in the first or the second week. There is a huge volume of it. We have too much data. We collect vast amounts of data, and in nearly every case, there is what we call the long tail. What we mean by that is that some data, a very small amount of data, we use a lot. Some data, medium amount of data, we use a bit. And most of the data that we hold, we hardly ever use. Okay, so you think about student records, we hold huge volumes of student records. Whenever I search by surname, I get records at Queen's going back, 40, 50 years in QSIS. There will be some students who have spectacularly disgraced themselves in the Holy Lands, and we'll do that this weekend, whose student accounts are accessed a lot by many disciplinary officers. And so they're used a lot. There will also be a smaller cohort, say all the current students, whose accounts are accessed a bit. Every now and again, the personal tutors are like, who's this person? Let me look up their photo. And then there'll be a huge volume of students who left 5 years ago whose details haven't been looked at for years. And this is represented by the diagram of the long tail. The idea being that there's a few things that we look at a lot. There's a lot of things that we look at very rarely. And by volume, most of the data exists in the long tail. Most of the data, by volume, is stuff that we hardly ever look at. Some is regularly accessed, some is not, and we store a lot of rubbish until it's not, until it's gold. Storage costs money, though. And certainly, the quicker storage is and the higher the availability, the more money it costs. So, very quick high availability storage, SSD drives, geographically replicated, available very close to you, very expensive per byte of data stored. Very slow storage, one old spinning hard drive in our core data center in Azerbaijan, much less expensive per byte stored, but not as quick and not as accessible. So one of the options, one of the ways in which companies that deal with large volumes of data deal with this is through using what's called data demotion model. And what we do is we define certain tiers or categories of data and what's available. So tier 1, very high speed data, data that's newly created, data that's recently accessed, we stick that on our high capacity, high speed, high expense front end servers. Tier 2, if data is not read for a certain period of time, it's automatically demoted. We say no one needs it. We move it back a tier. We don't anymore keep it in every single data center on SSDs and ready. We demote it down, perhaps for spinning platter drives and less data centers, so it might take longer to get. If someone requests that record, it takes more time to fetch it, sure. But what we then do is, because it's been read, we promote it back to tier 1 again. And we might do if it's read a certain number of times. And then finally, we can have other tiers below it. So we could say, well, okay, look, this file's not been read for a year. Let's demote it further down. So let's perhaps put it on a hard drive, and let's spin that hard drive down. Let's put that hard disk to sleep. Someone then tries to access that data. Okay, where is it? It's on this hard drive. Power up the drive, read the file, and copy it back up the tiers. And this is how Facebook works. If content hasn't been read for a long time, content goes onto hard drives, and those hard drives are put to sleep. It's why, when you're stalking people and you're looking at their pictures from 6 years ago, they take longer to load than the pictures recently. Yeah, I know who I'm looking at. And we can go beyond that. We could go further along the way. So if you look at IBM's example, IBM, a big provider of data storage, DB2, they have their mainframes. The way they work, and I've seen this working in large insurance companies, is the users just see a file system. You log on, you see documents, you see database, you see objects. You've got no idea where they're physically stored. But in reality, what happens is that objects which are not accessed for a long time, first of all, go on slower servers, and are secondly moved onto a tape within a tape robot. So in a basement somewhere, there's a big robot and a wall of tapes and a wall of drives. And what happens is that robot can go and find a tape and put it in a drive and do it. If that data hasn't been accessed for, say, a year, it ends up on a tape in a cupboard somewhere. And then what happens is when I access it, when I log in to that server and I say, please give me this record, the tape robot wakes up, goes and finds that tape, puts it into the drive, and then it's copied back onto the hard drive. So when I access that file, it might take 30 or 60 seconds for that process to be complete, but it's a lot more cost effective than storing it as we go along. Love life equals null. Who hurt you? Do you ever feel like calling out people who get up to leave lectures early? Yeah, but I think it would be quite cruel, especially when only one or two of them do it. Who knows what their story is? They might have a bus or a rabbit fight to go to or something like that. I don't know. Has anyone got any questions on this?